In this video, I'll be solving Math 2A midterm, first midterm that was given back in fall 2013. So hopefully this video can help you to see the types of problems that might appear or the level of difficulty of some of the problems, even just how to solve some of the problems. Okay, so this was given by one of the lecturers at UCI. I believe this person still teaches this. So hopefully for those of you that have this lecturer, this teacher, this can help you too. Okay, so Math 2A, midterm 1, let's begin. Okay, so actually I messed up on the first take of this video. So we're gonna go over here first. This is a two-part question. So let's go for part 1 first. This asks to find f prime of x for this f of x by the definition of the derivative. Okay, so how do we do that? Well, we know the definition of the derivative, limit definition, is f prime x is the limit as h goes to 0, f of x plus h minus f of x over h. Okay, that's the limit definition of the derivative. So let's plug in. Limit h goes to 0. So notice I don't drop the limit sign because I have not taken the limit yet. If you drop the limit notation, you might lose points. Depends on your professor or your teacher, if they are picky or not. Okay, so let's continue. We plug in f of x plus h. So wherever there's x, we plug in x plus h. So it'll be 1 over x plus h minus f of x, which is just 1 over x, all over h. We just used the limit definition of the derivative we plugged in. So how do we proceed from here? Well, the technique usually is we want to combine this into one single fraction instead of this complex fraction here. So how do we do that? We can multiply both the top and the bottom by x plus h times x. Okay, this is equivalent to 1, so this is valid to do. Okay, let's continue. I'm purposely writing big so it shows up well on the video. So when we distribute this term to the first one, the x plus h's would cancel. So we're left with x. Okay, and then next term, we have the minus sign there. We distribute this x plus h to 1 over x. The x's would cancel. We're left with x plus h inside the parentheses of this negative sign. Okay, so careful with your notation. All over h, x plus h, x. We leave the bottom alone for now. Okay, we can simplify. This x here would cancel out with this minus x here. On the top, we are left with minus h. Limit h goes to 0, minus h over h, x plus h, x. Okay, this h would cancel this h. We're left with a 1. Okay, and now we can take the limit. So when we plug in h as 0, what are we left with? We are left with minus 1 over x squared. Okay, and that is our answer. Okay, a quick way to check if you already know some of the content of Math 2A, like you took calculus in high school or something like that, or you took this class before, you know that you can use the power rule to quickly check that this is the answer. Power rule, this is the same thing as x to the minus 1 power. So when you do the power rule, it'll be minus 1, x to the minus 2 power, which is what we have over here. So we know that we got it correct. Okay. Now the second part of the problem, it says to find the equation of the tangent line to this f of x at x equals to 2. Okay. So remember the derivative is the slope of the tangent line. Okay? So with that knowledge, we know that the slope of this line is simply, we said derivative is slope of the tangent line. So f prime of 2 would be the slope of this tangent line at x is equal to 2. Okay, so f prime of 2, we found f prime to be minus 1 over x squared. So it'll be minus a fourth. Okay? We need also a point in order to write the equation of a line. We need a slope and we need a point. So we're given that the x coordinate is 2. What's the y coordinate? Well, f of x is 1 over x. So the y coordinate would be 1/2. Okay? We have a slope, we have a point, we can write the equation of a line. We can use point slope form. 1 minus half is minus a fourth. x minus 2. That is your answer right there. This problem did not say that you have to use slope-intercept form, but let's just do it. That'll be y minus half is minus a fourth x plus half, if we distribute that negative 1/4 to both terms on the right-hand side. So we would get y is minus a fourth x plus 1. That's your line in slope-intercept form. Okay, so that was not too bad. Let's move on. Number 2, we're given this is f. We have to sketch f prime, so let's say that's f. Okay? F prime, we just said in this first problem that derivative is slope of the tangent line. So we can do the easy points first. For example, at this maximum over here, if we draw a tangent line, what's the slope of this horizontal line? Notice I said horizontal line. That should immediately tell you that the slope is 0. So we know we have a 0 at that point. Similarly over here, slope of the tangent line at this minimum, again it's a horizontal line, slope is 0. Okay? Another thing I like to remember is when the function is increasing, the derivative is positive. And then the other way around. When the function is decreasing, the derivative is negative because, again, slope is increasing, derivative is positive. We keep drawing tangent lines. It's always a positive slope. And in fact, in this particular case, it's 0 here. As you move away from that minimum, it gets steeper and steeper, and it's the steepest when it's at the origin here. And then as it approaches to the max here, it gets less steep, so the slope gets smaller and smaller. Okay, so it'll look something like this. It's not steep, gets more steep. The plateau of the steepness is at the origin, and then it gets less steep. Okay, and then remember I said when a function's increasing, derivative is positive. Notice is how it's always positive when it's increasing. Okay, so when the function's decreasing, that's over here, the derivative is negative. Something like that. Okay, we're not giving anything beyond that, so we can just draw it like that. Similarly over here, before this minimum, the function was decreasing, so we know that the derivative is negative, so it looks something like that. Okay, this is your sketch of, f prime, not f double prime. That's just a sketch of f prime. Okay, let's move on. We're now asked to calculate limits. Let me shift this whole thing down. There we go. This one, limit as x goes to 2 of x minus 2 over square root 6 minus x minus 2. When we plug in x is 2, we get 0 on the top and 0 at the bottom. So we know that this is an indeterminate form. We have to do some more things to see if this limit exists or not. Okay, so typically the trick here when you have the square root, we like to use the conjugate. So remember what that is? It's just the square root plus 2 over square root plus 2. This is the conjugate. We multiply the top and bottom by the same thing to make it equivalent. This equal to 1. Okay, so what happens when we do that? Limit as x goes to 2. Notice I don't drop the limit sign still. Let's leave the top alone. We have this over, when we FOIL this out, the square root squared means the square root goes away. Plus 2 square root minus 2 square root, those would cancel. We're left with minus 4. Okay? We can rewrite the bottom as, so let's leave the top alone for now. This bottom is same thing as 6 minus 4 is 2, so it would be 2 minus x. Okay? 2 minus x is the same thing as negative x minus 2 like that. Again, just distribute the minus sign, it'll be 2 minus x. Same thing. Okay, so I did 2 steps in one kind of over here to simplify. But we want to do this because now we see that this can cancel. Okay, and now we can easily take the limit. So let's write one more step. Minus square root 6 minus x plus 2. Okay, this would be minus, that'll be 6 minus 2 is 4, so that's square root of 4 is 2, plus 2, which is 4, minus 4. That should be your answer. Let me double check. Yes, that's right. Okay. Not too bad. Just the key is, remember, use the conjugates. Okay, next one. We're asked to find this limit as x goes to 0, x to the fourth cosine 1 over x. So this one you have, in the techniques you learned in this class so far, you have no way to solve this except one particular theorem that you learned, which is the squeeze theorem. Okay, so how do we use the squeeze theorem? In this case, we know the cosine, the function, is bounded between -1 and 1. That's how the graph looks like, if you remember from the earlier sections of this unit, or even in high school math. Okay? Cosine is between -1 and 1. So cosine 1 over x is also between 1 and -1. Just the cosine itself is like that. Okay? We can multiply everywhere in this inequality by x to the fourth. So it looks like this. Okay? Now we can find the limits of the two bounds, because this looks like this now. So now let's find the limit of the two bounds. Limit as x goes to 0, we're finding the limit as x goes to 0 of the original problem, right? So let's find the limit of the two bounds at for the same x, okay? It'll be minus x to the fourth. This is simple, that's just 0. We also know limit x goes to 0 of the other bound, which is positive x to the fourth, is also 0. The limits are the same. Okay? Because the limits are the same by the squeeze theorem, we know that this limit is also 0. Okay? So we have to say squeeze theorem probably to get the point. So we showed this inequality relationship, we showed these limits of the two bounds. So by the squeeze theorem, okay, notice you have to say squeeze theorem, limit x goes to 0, x to the fourth, cosine 1 over x is also equal to 0. That should be your answer right there. Okay. Let's move on to the next one. Limit as x goes to 2 from the left, arc sine x over 2 over x squared plus x minus x. So the hint here is when you have this superscript of minus or plus, this one-sided limit probably means that it's an infinite limit. So let's figure that out first if it goes to infinity or minus infinity. When we plug in 2, arc sine of 2 over 2, where's the sine function 1 at what angle? That's pi over 2. At the bottom we get 4 plus 2 minus x, which is 0. So non-zero number over 0, that's infinite. So we convert into infinite limit. Now is it going to positive infinity or negative infinity? That's the next question. Okay? So how the strategy to do this is, well, let's first rewrite this a little bit. So we can keep the top the same, arc sine x over 2. The bottom, let's factor. That'll be x minus 2x plus 3. Okay, I just factored it. Okay? When we take the limit, this guy, as we said, would approach pi over 2 over, so let's do this guy first. X plus 3, as it approaches to 2, it would be 5. X minus 2, as it approaches 2, well, in this case, we're interested in 2 from the left. That means numbers smaller than 2. For example, 1.99. Okay? 1.99 minus 2, that is a negative number. So as we approach 2 from the left, it's going to be a small negative number. Okay, I want to write it like this. Okay, we have a positive number, we have a positive number here, we have one negative number. So the sign in the n would be negative. Okay, and then we said it was going to infinity. Well, we can see here too, that as we approach 2 from the left, this would be a small negative number still. And then these are both positive, so again, negative, and then it goes to infinity. So that's our answer. Negative infinity. Okay, next one. Limit as x goes to 0 of 3x squared over absolute value x. This one's just intimidating because of the absolute value sign, but the trick here is, remember absolute value x, it changes sign. So this is absolute value x. When x is less than 0, it's minus x over here. When x is greater than 0, is x. So that's the trick. As we approach 0, we're approaching from different curves. So the idea is to break this up into two limits. Limit as x approaches 0 from the left, and then limit as x approaches to 0 from the right. Okay, two limits. Remember, when the limit from the left equals limit from the right, the limit exists. Okay, of two-side limit exists. Okay, so as I said, when we approach 0 from the left, we're on this side of the curve, which is minus x, so we can rewrite this as limit x goes to 0 from the left, 3x squared over minus x. Okay? This is simply just 0, the limit, because this would cancel with one of those. We're left with 3x minus 3x, limit as x goes to 0 of minus 3x. So maybe let me write it a little more clear. X goes to 0 from the left of minus 3x. This is 0. Okay? Similarly, for this, 0 from the right, again, we're on this side of the curve, which is plus x. 3x squared over positive x. And again, we're just looking for the limit as x goes to 0 from the right of 3x. This limit is 0. Because the limit from the left equals the limit from the right, then this guy is 0. Okay? Or it's also 0. It'll be the same limits. I should say that a little more clearly. Okay? So that's that problem. Next one over here, limit as x goes to negative infinity of square root 4x squared minus 1 over 3x plus 1. Okay. This one, the clue is x goes to infinity or minus infinity. This likely means a horizontal asymptote. Okay? And there's a quick way to eyeball this. Okay? So I'll teach you that first, and then we'll go to actually solve it. Remember, when it's a polynomial over another polynomial, you could do the degree test. Okay? So we look at the biggest term. Okay? Because everything else would be insignificant. For example, let's just take this example here. 3x, as x goes to infinity, this term would dominate, this one doesn't matter. Same thing at the top, a similar thing at the top, 4x squared would dominate over a minus 1 as x goes to infinity, or minus infinity. Okay, so we care about the biggest term, which will be 4x squared and 3x, okay? This is the same thing as plus minus 2x over 3x, okay? The degree of the top and the bottom are the same. So we take the ratio of the leading coefficient. So it'll be plus 2/3 or minus 2/3. That's your way to eyeball this answer. Okay, so let's find out which one it is. The actual way to solve this is, that the professor's probably expecting for you, we like it when limits to infinity are something like 1 over x, or 1 over x squared, or 1 over x to some power. Because as x goes to infinity, this term goes to 0, this term goes to 0. So yeah, that's the idea. We want to write something like that. So over here, how to do that? Let's do limit x goes to minus infinity. I like to just factor out the biggest degree from the top and the bottom, so it'll be something like this. We factor out x squared on the top, that'll be 4 minus 1 over x squared. Okay? Over the bottom, the biggest term is x, so it'll be 3 plus 1 over x. Okay? Again, I just factor out the biggest degree, so factor out x squared on the top, and x at the bottom. Okay? Now I like to use our properties of limits to break this up into two limits. Limit as x goes to minus infinity, square root x squared over x, times limit x goes to minus infinity of the remainder, 4 minus 1 over x squared over 3 plus 1 over x. Okay, this is properties of limits. So you can break up a product of two limits. A product of two functions, we can break it out as the limit of the two functions multiplied together. Okay? Now, this limit is easy because remember, we want something like this. this term would go away. This term would also go away. So we're left with root 4 over 3, which is 2/3. Here, we have to be careful. We can simplify this because square root of x squared is plus minus x. Okay, is it plus x or minus x? Well, as x goes to minus infinity, it will be minus x. Okay, so we can rewrite this as limit x goes to minus infinity minus x over x times 2/3. So this is just 1. Those would cancel. So we are left with minus 2/3 as an answer. And that's in line with our initial eyeball. It's plus or minus 2/3. We found out it's minus 2/3. Okay, let's move on. Number 4, part A is this function continuous at x equals 2. Why or why not? Okay. This we can immediately tell that just by the domain of f, x cannot be equal to 2. Okay? Therefore, since x cannot be equal to 2, not continuous at 2. So, no. We can say f of 2 is undefined, or does not exist. F of 2 does not exist. That's our reason. As simple as that. It's either asymptote or a whole at x is equal to 2. So it's not continuous at x equals to 2. Okay? Now it's taking that same guy, but it's putting it in a new function, and kind of piecewise. We have this guy, x squared minus x minus 2 over x minus 2, for x is not equal to 2. And then when x equals to 2, it's some value c. And we're asked what value of c will make this guy continuous at x equals to 2. Okay? So the clue here is what I said earlier. It's either asymptote or whole. It's actually a whole. So let's take the limit as x goes to 2 of this guy up here to see what it approaches. Okay? This is simply the limit as x goes to 2. If we factor it, that will be x minus 2, x plus 1 over x minus 2. This would cancel. We take the limit of x goes to 2 of x plus 1. That is just 3. Okay? So if c is 3, then f is continuous at x equals to 2. Oh, cut off. C is 3. Okay, we found the limit because we saw that it was a hole at x equals to 2. If we simply fill in that hole with the limit, then it makes it continuous. As simple as that. Okay. Next, we're asked to do some interpretation of what derivative is. Capital C of T represents the temperature in degrees Fahrenheit of a warm soda T minutes after it's placed in a refrigerator. So it asks us to find the practical meaning of T prime of 2. Okay. Remember, derivative is rate of change. Okay. So what is being changed? The temperature is being changed when it's put in the fridge. Okay. So T prime, again, rate of change is, we can say, rate of change of the soda's temperature. Okay, that's T prime of T. T prime of 2 is specifically at time is 2, which is 2 minutes after it's placed in the fridge. So rate of change of the soda's temperature after 2 minutes. That's our answer for part A. Units of T prime of 2, again, it's rate of change. So what's being changed? Temperature, those units are degrees Fahrenheit. What's the unit of time? It's minutes. So degrees Fahrenheit per minute. Okay. And then it asks, would you expect T prime of 2 to be positive or negative, and why? Well, T is the temperature. T is decreasing. So we expect T prime to be negative because temperature is decreasing, let's say. Okay? We can even draw a simple graph. If, like for example, this is T of T, this is T, temperature of the soda, which should gradually decrease. T prime of 2, remember T prime is slope of the tangent line, or derivative is also slope of the tangent line. If you interpret it graphically, the slope is always negative. So that's another way to interpret this, or to get to this answer. Okay. Let's move on. We're asked to find the domain, horizontal, and vertical asymptotes of these functions. No work is needed, okay? Domain, the bottom of this fraction cannot be 0, so x cannot equal to -2. Horizontal asymptote, we can do the degree test because this is a polynomial over a polynomial. Degree at the top is 0, degree at the bottom is 1, degree at the top is less than the degree of the bottom, so that means horizontal asymptote at y equals 0. Vertical asymptote, x is -2, similar to the domain. Okay. Next one, domain, the bottom cannot equal to 0. Well, the bottom can never equal to 0, so it's all real numbers. Or if you want your interval notation, -infinity to infinity, something like that. Okay, so if you don't know why, x squared plus 1 has to be greater than 0, so meaning x squared has to be greater than -1, or x squared plus 1 cannot equal to 0, sorry. X squared cannot equal to -1, and unless we're talking about imaginary numbers, that can never happen because when you square something, it's always positive. So x squared can never equal to -1. So all values are valid, -infinity to infinity. And actually, you can just double check also what happens if it's 0. When it's 0, x is 0, 0 plus 1 is 1, which is always greater than 0. Which is always not equal to 0, sorry. So, all real numbers. Horizontal asymptote, degree test, the two degrees are the same, so we take the ratio of the leading coefficients, which is y is equal to 2 over 1, which is y equals 2. Vertical asymptote, none. Next, domain, x cannot equal to 3. Horizontal asymptote, degree at the top is bigger than the degree of the bottom, so there's no horizontal asymptote. There is a slant asymptote, but we're not asked that, so we're okay. Vertical asymptote, x equals 3. Next, k of x is natural log x plus 3. Domain, x plus 3 has to be greater than 0. So x has to be greater than -3. Okay? The log, inside the log has to be greater than 0. Okay? Horizontal asymptote, the log does not have any. None. Vertical asymptote, this log is shifted by 3 to the left. So remember, the log, or even the natural log, has an asymptote at x equals to 0. So now this is shifted to the left by 3. So x is -3. Okay. Good. Now we're given this graph of f. Okay, let me center it on the screen. Okay, and we're asked to find all these limits. Okay, so let's go one by one. We're asked to find limit as x goes to -1 from the left of f of x. So here's -1, x is -1. So as we traverse -1 from the left, that's this curve over here, what's that limit? It's approaching 3. -1 from the right-hand side. So again, here's -1. We traverse it from the right. That's going to this value, which is 2. Okay? Now the two-sided limit, when there's no superscript, that means it's from the left and from the right. Well, the limit from the left is not equal to the limit from the right, so this does not exist. Okay? 3 from the left, here's 3. We traverse 3 from the left, that would be -1. 3 from the right, that's this guy, which is 2. And then 3 from both sides, again, limit from the left is not equal to limit from the right. This guy does not exist. 4 from the left, that is this guy here, which is -2. 4 from the right, that's this guy here again, so that again is -2. 4 from both sides. Well, here the limit from the left equals limit from the right. So this is also minus 2. Okay, and this one's the easy one. Limit as x goes to 2. That's here. This is continuous there, so that's easy. That's just 1. Okay, so that's how you do this type of problem when you look at a graph and you find these limits. Okay? Next, this is the last problem. We're asked to find all points of discontinuity in number 7, and you have to say why. Okay? So let's go back to the graph. We know that you can think of discontinuity as where do you have to lift your pen or pencil when you draw the graph. That's over here, there's a jump there. That's over here, there's a jump there. And then over here, it's discontinuous there because there's no value there. So technically you have to lift and then draw again. Okay? So let's write that down. That's when x is equal to minus 1. X is equal to, that will be 3. And then x is equal to 4, which is over there. We have to say y for each. Remember the definition of continuity: limit as x goes to some value a of f of x. If this is true, then it's continuous. Okay? Well, none of these satisfy this requirement because for this one, x is minus 1, the limit does not even exist because the two one-side limits are not equal. So that's the answer. Limit as x goes to minus 1 f of x does not exist. Same reason for x is 3. Limit from the left does not equal limit from the right, so there's no way that this can even happen. Limit x goes to 3 f of x also does not exist. This one is a different reason. This is simply, well, the limit exists from both sides, and it's the same value from both sides, so the limit exists. But the function isn't even defined at x is 4. So you can say f of 4 is undefined or f of 4 does not exist. That's fine. And that's your answer. Okay? So that was that, but we have one bonus problem. This was from the second version of this midterm, because you know professors like to give multiple versions to prevent cheating. Let's just solve this too. I thought this was a good problem. Limit as x goes to 1 from the right, arctan x of x squared plus 7x minus 8. Again, the hint here is the superscript of plus or minus. Likely means it's an infinite limit, so let's confirm. When we plug in 1, arctan of 1, that's why I like this problem, because it's testing if you remember the arctan of 1. That is pi over 4. Okay? And then the bottom, if you plug in 1, that'll be 1 plus 7, which is 8, minus 8 is 0. So non-zero over 0, infinite. Okay, so we confirm. Now again, we have to figure out if it's going to positive infinity or negative infinity. So let's rewrite the bottom to help us out. If we factor it, that will be x minus 1, x plus 8. Sorry, x minus 8 if we factor it. Does that look right? That doesn't look right. Let me see if I wrote the problem correctly. Okay, I did write it correctly. Okay, so I just factored it wrong. Limit as x goes to 1 from the right, arctan x over, this is simply just, if we factor it out, it would be x plus 8, x minus 1. There has to be x minus 1. Yes, that's right. Okay. Sorry about that. Okay, so again, we know it's an infinite limit. Is it going to positive infinity or negative infinity is the answer. So as we approach 1 from the right, this one we already said goes to pi over 4. Over 1 from the right, this would be approaching 9. This guy, every we approach 1 from the right, it's 0, but then again, 1 from the right. So numbers, in this case, bigger than 1. So for example, 1.001, that's bigger than 1, but that's not 1 yet. So that would be a small positive number. Okay? The sign of everything here is positive, so we know that this is going to positive infinity. I would just put plus to make it very explicit that you're going to positive infinity. Okay, that's all I have for this video. So if you have any questions, please feel free to leave it in the comments. Otherwise, if you found this video helpful, please smash that like button and please subscribe to this channel to see more solutions to calculus problems or math problems. I might do some more different math topics in the future.